Okay, hello everyone. I'm recording this lecture for our February the 6th class, which I've been missing. And this is going to be about map projection. And I'm going to show you some of the slides here. And just to let you know the system here, we have the PowerPoint. And then we have the slideshow. I'm going to go through some of the slides through the slideshow. Also, the software or Zoom here allows us to do what we call the whiteboard, which is really very helpful demonstrating some of the stuff or writing. So this is basically what this will be about. This is just going to be a test. I want to make sure that everything is working, and I'll do the lecture in different parts just to make sure it's capturing every single part. Plus, also, I don't want to make a big file and then you have problems downloading it or I have problems uploading it. So let me pause here for a few minutes and then get back to you, and then we'll take it from there. Okay, so what's the idea about map projection here? So let's go back to our basic understanding of the Earth, that the Earth is a sphere or an ellipsoid, or it's actually not a sphere or an ellipsoid, or even a geoid. On the Earth, we've talked about what we call the unprojected coordinates. What are the unprojected coordinates? These are our lambda and phi, the longitude and the latitude of any point. So any point on the Earth has the lambda and the phi, and we did talk about what's lambda. It's the angle between the meridian of Greenwich. If we draw the, let me use the whiteboard here instead. I'm just going to do it in the whiteboard to refresh our minds with lambda and phi, or latitude and longitude, which I assume all of us knew about, but just in case you forgot. And I'm going to go to the whiteboard, draw a circle, and then have this nice sketch tool. Okay, so if you have the equator and you have a point here, this is the North Pole. So for any point, you draw a line from the point to the equator that defines your phi. Again, simple as for a sphere. And then if you think and you remember about the lambda, wrong color. This is the equator. We are looking from top now, so we are looking this way. And the North Pole here is going to be only a point, if you remember. And excuse me for the drawings here. So this is the North Pole and the center of the Earth. Why is it exactly here? Because we are looking from the top. And then the important thing for us is Greenwich. So we defined the zero longitude to align with a city called, or a point called Greenwich. That's our zero. And then from there, we started defining our longitudes. This is our longitude here. In all cases, these are the coordinates, and then we have h, but for map projection and simplicity, we are going to use that, assume that h is 0. So all the points are going to be on the sphere, just for the simplicity of it. So when we do this here, these are what we call the unprojected coordinates, degrees of latitude and degrees of longitude on the globe. But of course, you can go to a site, have the globe, or have a scale of the globe with you. That can't be done. So what we need to do is we need to project our coordinates. We need to convert these coordinates into a planar coordinates. We need to put our lat long here into a planar coordinate. Convert this from the sphere to a plane. So then you can fold it, you can take it to the side, you can scan it, you can do a lot of things. You can do a lot of things with that. So that's the purpose of today's lab. How do we do this? We do this through a set of mathematical equations. There are very sophisticated and complex mathematical equations, and there are simple ones. I'm going to show you some of the simple ones that I'll ask you guys to do something with them in the homework. But the basic idea is to convert your coordinates from 3D, whether x, y, z, or lat, long, height. Remember, we were able to convert between lat, long, height, and x, y, z. So from either of these to a 2D map, to an XY, or what we are going to call northing, easting. So to write it down in a very broad terms here, we would like to convert lat long, or long lat height, we are assuming the height is 0, to northing, easting. Let's now forget about XY. We don't really use XY in surveying. And longitude, latitude, and height could also be represented by X, Y, Z. Let me actually clear the board and put it in a more text format. So we have X, Y, Z, which could be also represented as our lambda, our phi, our h. And we are saying that we are going to assume h is 0, but in general, h could have a value. And the purpose of the map projection is to convert these into northing and easting. How is that done? That's the topic. Before, I think that will get us wrong screen. So before we start doing that, I just want to remind you about some few important comments here about map projection. So the first thing is, usually when you use a topo map, you will see different coordinate systems, and you have to be very careful. You will see the GCS, or the unprojected geographic coordinate system. That's a name for them. So you'll see the latitude, longitude, which are okay, but there is a problem with that. And you will also see state plane. In most cases, you will see the state plane coordinate system. We'll talk about what's the state plane coordinate system. And you'll see another coordinate system called the UTM. Now, if you look here at this one, let me grab, it's easier to work here than work in the slideshow. If you looked here at this coordinate system, what will you realize here is it has easting. So that's important. Or this one here, it has northing. So you have to specify also whether your coordinates are easting, northing, or sorry, easting, westing, or northing and south. Another important thing also for the state plane and the UTM, what units are we using? UTM, Universal Transverse Mercator, we'll talk about it, uses meter. State plane, you have to be careful. Which state plane are we talking about? We'll talk about that in few, or actually maybe in the next lecture. So these are some of the important comments. Just to summarize, GCS, the unprojected or the geographic coordinate systems that are defined in degrees, minutes, seconds. Plus, we have different types of projected systems. The most common two are state plane, which is this one here, to the left, oops, bottom, to the left bottom here, and this one, the UTM, which is in the middle of the screen here. So you have to be careful which one are we using. The units are important, whether it's south, north, which datum. That's a very important thing. if you remember when we were talking about this shape of the Earth, we said, well, the shape of the Earth looks like this, and we can't really find or fit one ellipsoid to it. So what we ended up doing is fitting different ellipsoids. We end up fitting different ellipsoids. So we had one ellipsoid maybe that looked like this, Clark, for example. We had another ellipsoid that let's use green, that looked like this, NAD. Let's type this one as North American datum of 83. The other one is NAD 27. So we had different datums here. We had different ellipsoids. And when we have different ellipsoids and we do the map projection, of course, the projected coordinates are going to be different. Even the latitude, longitudes will be different. So that's why one of the important things when we do our maps, like the topo maps here, and you look at it, it says this topo map is based on the WGS 84. So that's the base of this map projection. It's an NAD 83, and it's using the WGS 84. That is very important. And then it also tells you what type of map projection is being used. We'll talk about these two things. But for now, please make sure when you read a map, don't just read it as numbers. You have to know the datum that you are using. You have to know what ellipsoid you are using. So these two are very important, and we've talked about them before. Another important comment here, in California, Section 8817 of the Public Resource Code here requires that all new surveys that you are doing should be using or should be projected or should be mapped according to the CCS 83. What's this? We'll talk about it later. It's just the California Coordinate System of 1983. This coordinate system is based on a datum, NAD 83. So we'll talk a little bit in more details about this. But these three slides that I just talked about set the ground for map projection. These three slides show you the importance of map projection, show you what type of map projection, shows you actually that the Public Resource Code, and in different states, you find this in the statutes, you find it in the Public Resource Codes, you find it in different places. They mandate certain coordinate systems to be used. Okay, what is map projection? And why is map projection important? We've talked about that in the last few slides. But what is map projection? Map projection is actually going to be a rendering of the Earth. So let's take a look here. Systematic rendering. By rendering, you are going to project this map into a flat surface. And systematic because in all map projections, you cannot just keep picking and choosing. You cannot say, well, this part of the map, I'm going to project it with this type of map projection. This point, I'm going to project it differently. This point is not shown on the map, so I put it somewhere so that people can see it. You cannot do that. You are going to use a systematic way. And this systematic way translates into a math model. So we'll have different math models that we apply for all places. We apply for all latitude, longitudes. Some of the points might not be projected. We have to figure that, and we have to figure how to deal with it. Some of the points might have huge distortion, so we'll have to think about it, as you will see. But in the end, it's systematic. It's not that we pick for different points, different map projection, regardless of how the map will look like. Again, you are going to set your criteria, your goal, but you can't really say all points will fulfill the criteria. Okay. So we talk now about rendering. You remember when I showed you the lat long to east north? That's really what we are doing. This systematic rendering is going to be through some math models here. And I'll have some nice map projection, simple ones, very simple ones, I mean, like, the big ones or the ones that uses even the ellipsoid are very big equations. And I mean, most of them now are computerized, and there are a lot of software and websites that can do this for you. But we still need to understand the basics. We still need to understand the fundamentals. So that's why I'm going to give you a simple homework. I think it's a simple homework where you can plot such things. Okay, so we try to define this function and then plot it. And once we plot it, we'll find that there are points that are not projected. So how can we deal with them? Or there are points that have high distortion. Again, distortion is a big term here. Distortion really is the key factor which map projection are using. Okay. So our 3D surface is going to be projected into a surface that could be folded and made a plane surface. So let's look at this here. New sure. So we have, again, just very conceptual here. We have the 3D surface of the Earth. I usually just put these two circles here saying that this is the 3D, and we would like to project it into a surface that eventually we can, this surface, eventually we can unfold it or make a 2D plan from it. So how does this work? That's the map projection. What is this surface? What is this surface here? That's what we call the developed surface or developed surface here. And there are different terms for it, but that's what we call the developed or developable surface here. So again, what is this surface? What could this surface be? Well, this surface could be one of these three surfaces. And there are some math models that do not use surfaces, but this surface is basically one of these three. It could be a cylinder. And once you have a cylinder here, it is very easy to unfold the cylinder. If you have a cylinder, and then let's go back to the whiteboard here. So if you use the cylinder here, it's going to look something like this. This is how the cylinder will look like. And then you can easily cut it at any axis and then unfold it so you get the shape that you are looking for once you unfold it. So that's one surface. That's the cylinder. Another surface that we use is the cone. Same concept. This is the base of the cone, and then this is the cone here, a 3D cone, and then you can come at any line, cut it, so you cut here, and then you unfold that. When you unfold that, you will get the unfolded cone here, so you'll get something that looks like this. After unfolding that, so we'll have maps that look like this. That's what we call the conical projection. The third one is what we call the azimuthal projection. So we have the Earth again in 3D. I'm using the mouse here, so it's a little bit difficult to draw the 3D circle, but we have the 3D surface. And now, instead of using a cone or a cylinder, we are going to use a flat plane. And we've put the flat plane on top of the Earth. And then we start projecting, but eventually we already have the flat plane. So there isn't really anything that we need to unfold. It's directly a flat plane here. So that's the third surface here. So these three surfaces, the cone, the azimuthal, the plane, and cylinder are the ones we use here. These are what we call the different map projection. And you see here the different ways the Earth, the same area, the same part of the Earth will look like. In a cylinder, if you put the cylinder this way, this is how it will be projected. You see the latitude, longitudes. That's really the key here for the success or for the distortion of this map projection. You see the cone here. You see the cone here when you project it to the cone, how the latitude, longitudes. Look at the latitude, longitudes, how they are converging toward the North Pole. Unlike here, they are parallel. And if you looked here, they are parallel, yes, but I'm going to make this one the biggest here and bring it to the front. Why? To show you here, you see the distances here, how the distances are changing. So this distance is an equal distance. This is, let's say, latitude 30, 35, 40. You see that the distance is increasing. The distance is not constant here. By the end, when you approach all the way to the North Pole, this distance will go to infinity, meaning you can't really project the North Pole. And I'll show you this in more details. Unlike this one here, which is the conical, you see this distance, distance. You kind of see the distances are increasing, but at the end, you still have a point for the North Pole. So you still can project the North Pole. However, you see that your circles here are not straight lines. They are circles, true circles. Which one is better? It really depends. What are the purpose of the map, plus what is the allowed distortion? Are you allowing distortion on areas, or are you allowing distortions in angles? We'll talk about this in later. If you'd like to look at this one, the azimuthal, this is how it looks like. You see the distances here, how they are increasing, but you still get your North Pole. Another interesting thing about this one here is you see how it looks like it's curved somehow. The angles here are a little curved. Unlike this, the angles are 90 degrees. Another key thing, well, both are actually 90 degrees, but you see the curvature here. These are straight lines. That's what I meant. These are straight lines with circles. These are curves with curves. So that's what I was talking about. Now, if you talk about, if you look at the three of them here, you see that in the eastern direction, the distances between the longitudes are the same. You see, this is equal here going this way, and this here is equal this way, and this is equal this way. However, when you go up this distance, again, that's just a very basic intro here. You see this distance here is equal to this distance here. But when you go up, they start getting closer, and this distance and this distance start getting smaller. We'll talk about it in more details. But the point that I just want to show you is that the geometrical relationship, the whole purpose of this slide, if you are summarizing this slide, the geometric relationships between the latitudes and the longitudes differs from one map projection to another map projection. How, why, what's exactly going on, that will be detailed through this lecture. So don't worry about all this thing if you didn't really get all the details now. Once we are done with this lecture, you should be able to get it. Now, you look here, another interesting thing. You look here that we put the cylinder with the axis vertical. We put the cone with a vertical axis, or an axis that, again, in our geodesy, a vertical axis here is an axis that goes through both North Pole and South Pole. And we put the plane here touching or tangent to the Earth at the North Pole. But there are other ways to attach this developable surface. These are different ways. Look at the first three here, or let's look first at 1, 2 here, these two. This is if we place the developable surface vertically. You see how the latitude, longitudes would look like. If we placed it horizontally, meaning the axis is coming horizontal, meaning that the axis of this, let me put it in paint here. And then share the paint and talk about it. Okay, so here you see that our axis here is vertical axis for the cylinder. For the cone, it's the same thing. This is the axis. And you kind of see how the latitude, longitudes will look like. If we placed our axis horizontally, this is how the latitude, longitudes will look like. If we placed it for the cone this way, this is how our latitude, longitudes look like. Again, this is very rarely used. That's why I highlighted this, but I'm showing you the concept. How will they look like? Should you know actually all these? Will I tell you, well, project the Earth using a regular cylinder? No, you don't really need to worry about putting these on your cheat sheet. But you need to know that there are different ways to orient your developable surface. There are different ways to project the Earth in general. And then you can also put it in an oblique. There are some cases that you will see some oblique map projections. So it really differs. What is the purpose of the map and what distortion are you allowed? If you looked at the azimuthal, you can set a plane like this here. This is the perpendicular axis to it, or you can set it tangent and horizontal plane, or you can set it tangent and oblique. So different ways that you can see here. And there are also what we call artificial projections. These projections here, the Robson, the sinusoidal, which are the ones that are mainly used, these are not based on any type of a developable surface. You remember, these ones all have developable surface here. These all have a surface that is attached to the Earth, and we can project it with the developable surface. These ones, we don't really have a developable surface. These are just based on math equations. N or X is a function of lat long. That's it. But there isn't really any way to show what the developable surface is. Some mathematicians or some scientists came up with, or geodesists, if you would like to call them geodesists also, did come with a math model that doesn't really have any type of developable surfaces here. Okay, let's go back to our PowerPoint. Okay, so back here to our lecture. We just talked about the different shapes, the different projection models. Now let's talk a little bit more about the cylindrical projections, and I'm here highlighting two of the very most important ones, Mercator and transverse Mercator. So I'm going to grab Mercator here. Okay, let's take this here, go to Paint, prepare it on Paint, so you guys can see what's going on, and then we'll talk about it in more details. Give me a second here, and I can share the screen, there is no problems. Okay, and Paint. So this is the Mercator here. The resolution might not be that good, but it gives you the general idea. So here are some of the properties about Mercator, and I might not be asking you, or I will not be asking you actually, to sketch how the Earth looks like in different projections, but these properties that I'm going to talk about, please take notes for them. I in purpose didn't write them down so that you guys can take notes and know what's going on with these properties. So here is the first property. The equator in Mercator, as you'll see, is projected as a straight line. So that's number one. You see, it's very obvious that this is the cylinder, this is the equator. When you cut, you will see that you'll get something like this. This circle is going to be projected as a straight line. That's number one. Now, you are going to cut at one of the axes here. Let me not go over it. Let's say you cut, your scissor is going to go through this line here. This line is this line here. This is where you cut. And usually the best place to cut the cylinder is at the Greenwich. So when I take this one, it's going to look like this. This is the cut. That's not really very necessarily, but in general, that's the case here. Now, here are some of the very important properties. Let's take another line here. Let me use another color. Let's use, I have usually some difficulties for the colors here because of the background, but let's use this color here. Okay, where is this line going to be projected? I hear some of you are saying, which is right, it's going to be projected parallel to our longitude, parallel to the main meridian here, which is going to be projected here. If I have another line to the other side, it's going to be projected, the trunk, that's going to be projected like this. And then if you look at it, this is our line. So what do we conclude from that? The longitudinal circles, these were circles. If you remember, these were circles on the sphere here. These were circles. This one and this one, these are parts of circles. These circles, the longitudinal circles, are projected as straight lines. So please take another note here. Longitudinal circles are projected as straight lines. Very interesting property here. If you take this next one, so if you take the next longitude, like this one, and then the one after, like this one, you see that the distances between, there is one that I missed here, the distances between the longitudinal circles, let me use another color, this distance, if I draw a line here, this distance between equal interval longitudinal lines is going to be constant. So the distances between the longitudinal lines is constant. This is another property. So we've talked about these lines being parallel and straight lines. We've talked about the spacing between these lines to be constant. Please write down these properties. You will be tested on them. Okay, what else do we have? Well, let's now look at the latitude circles, and let's pick orange, for example. So we have the latitude circles. Where is this circle going to be projected? I hear some of you are saying it correctly. It's going to be projected as a straight line above the equator. Where is the other one going to be projected? Another straight line above the equator. But here is the difference. If I projected this one on this nice sketch, it's going to be here. And if I projected this one here, it's going to be here. And the other ones that you might see here is this, this. Now, here is the thing here. Here is the thing. You see the distances between these lines? It's getting longer or shorter? It's getting longer. The further you go up, the further you go north, the distances between the latitude circles is going to increase until you hit the North Pole here. Where is the North Pole? It's infinity. You have to project all the way infinity. So you can't see it actually. So two more properties here. Please write your notes. Parallel circles are projected as straight lines. That's number 4. Number 5, the distances between these lines is increasing as you go north or south from the equator. And of course, if you would like to say number 6, the North Pole is not projected, that's fine. So these are the 6 properties. Let's summarize them. Equator is projected as a straight line. Okay, of course, equator circle. Parallel circles are projected as straight lines. However, number 3, I didn't put that, well, let me put them in order. So number 1 is the equator is projected as a straight line. Check. Number 2, the distance or the distances between the, number 2, the longitudinal circles are projected as straight lines. You see it here. That's the second one. Number 3, the spacing or the distance between the longitudinal circle when projected is going to be fixed or the same. That's the third one. Number 4, our latitude circles are going to be projected as straight lines. You see the circles are coming as straight lines. Check. Number 5, the distance between the latitude circles is increasing as you go north or south from the equator. That's the 5th one. The last one, if you consider this as another one, the North Pole and the South Pole for sure are not going to be projected. So this is the Mercator projection. Very interesting. Make sure you got these 6. Okay, now let me clear this and do another one and go back. It's very critical what you are sharing here. We're still here, and let's take the transverse Mercator. The reason I'm saying it's very critical, I did record this lecture and I forgot at one point to share the screen, so it was just on the previous screen and not showing all the details I'm doing. So that's why I need to go back and forth. Let's look at the transverse Mercator. Here is how it looks like, and then I'm going just to make it bigger so that you can see the different parts. Okay, let's again start counting. Number 1, the equator, where, hello, oops, Control Z, Control V, okay, glad I got it. Hopefully this wouldn't affect your learning process here, the Control X or these things. Okay. So where is the equator? The equator was a circle here. So this is the equator. It's going to be projected as a straight line. You see where the equator is? Very interesting. This is the equator. You see how the equator looks like. So this is the first property. And then where are the longitudinal or the latitude? Let's start with the latitudes first. The latitudes, we used orange before. So this is latitude, latitude, latitude. Now, due to the shape and orientation of the developable surface here, these latitudes are going to be projected as these ellipses here. Hopefully this will work. You see, yep, perfect. You see the ellipse here, this is one of the latitudes. That's the second one. You see, this is the second latitude. And then you go further and you get the next latitude, it's going to go like an ellipse. That doesn't have to do anything. Remember, we are using the sphere here as our model. That doesn't have to do anything with the ellipsoidal shape of the Earth. That's just the way the projection will look like. You project a sphere on a cylinder. And it starts going all the way like this until you get all the way to the North Pole. Again, that doesn't have to do anything with what we've talked about before as the Earth as ellipse. So that just is the way a sphere is, or circles on a sphere are projected on a transverse cylinder. So this is the second property here, if we will mark this down. Number 2, the latitude circles are projected as ellipses. Okay, how about the longitudinal circle? This is the principal meridian here. You see, this is one of the principal meridians here, or one of the meridians. So where is this going to be projected? This line here, or this circle longitude, is going to be projected as a straight line. This is where you are going to do the cut here. You do the cut here, it's going to be as a straight line. And then what? So you see the North Pole, interesting. You see the North Pole here and the South Pole here are projected. Perfect. If you would like to add this as this is 3 and this is 4 here, so they are both projected, or let's just say that this is 3 here. Both the North Pole and the South Pole are projected, and then number 4, the principal meridian. Here is the principal meridian. Here doesn't have to do anything with our public land surveying system. I just called it the principal meridian as the meridian where it touches here. So just to make sure we can call the principal meridian. This is the meridian that, or the longitude circle that the cylinder is going to touch or be tangent to the sphere. So whenever it's going to be tangent, it's going to be projected as this straight line. You see it clearly. Okay, what else do we have? And then where are the other ones? Let's take a look at the other ones. The other ones will all be the curves that are coming from the North or the South Pole. Let me draw it here for clarity here, because this one is already getting the mess here. So I'm going to draw these ones. Let's use pink. Let's get the second one. It's going to look something like this. And then the next one. It's going to look something like this from this side. And if I draw the other side, which is going to be dotted, because you can't see it really, this is the other end of it. And then the next one. And so on. You get them as these curves here. And again, you don't really need to dig much into how these curves or the math equations. And then you have other ones like this. And so on. East and north. Okay. I was just going to say if there are any questions. I mean, you can, of course, as we will set it, do the questions here. So let me draw these again, because I know these might get a little bit complicated here. You see this one, let's get back to another color. This is one of the parallels here. It's going to be projected as a curve here. So hopefully that makes sense. And these latitudes are going to be projected as these ellipses here. Okay. And I think let's just put this as one more property and summarize them. This is going to be number 5. So what are the properties we have? The first property is the ellipse is going to be projected as a straight line. Second property is these latitude circles are going to be projected as ellipses, either here or here, depending on which part of the earth you are in. And then the third property, we said that the principal meridian, that doesn't have to do anything with our principal meridian in the public land surveying system. That's the principal meridian where where the sphere is going to touch or be tangent to the ellipse. That's going to be projected as a straight line. Other longitudes, that are in pink, other longitude circles that are in pink are going to be projected as curves like this. What I can do, for example, that's a good thing that I can do, is give you sketches and ask you to label them. That's another way. So I can ask you questions like where or how this is going to be projected, or I can give you sketches and ask you where are the latitudes, where are the longitudes, where is the principal meridian, where is the equator, and so on. So just be ready for such things. But I'm not going to ask you to do sketches, because then sketches might not be the best way that you can describe your knowledge. Okay, so going back to PowerPoint, okay, share. Let's look at the next one, the conic projection. Let's take a look at this one here. Let me grab this one and go to Paint. Then I need to share Paint. Make sure I don't forget that. And I gave you some names for some of the projections. Again, you don't really need to memorize these names. You don't really need to know this one is called this, except very few that we have to know that I will highlight, but you don't need to know all of them. Okay, so this is how it looks like. What's going on here is the following. First thing is, let me make sure I have the right colors, the right things here. This is the equator. This is the equator. Where is the equator projected when we have a cone or a conical projection? It's going to be projected as a circle. You see, this is a circle. And the center of the circle is the center of the cone, which is the North Pole. So first thing is where the equator is going to be projected. It's going to be projected as a circle, or actually as a part of the circle if you don't complete the whole projection. And number two, the center of the circle is going to be the North Pole, which is here. You just think about you are looking this way. Very simple. If you are looking this way, and I'm going to show you an animation here how the projection works. If you are looking this way, then you see the circle, you see the epic of the cone, which is going to be the North Pole. Okay, how about the other latitudes? We are using pink, so let's use pink here. These are the latitudes. So you look at the latitudes here, and these are your latitudes. This is one. So they are all concentric circles, meaning these circles are sharing the same center. These circles are all sharing the same center. So that's one of the properties, or if you'd like to call it the third property here, that this is the third property here, that all the different latitude circles are going to be concentric, and meaning they all share the same center, and they are all going to be circles. If you look downward below the equator, then these circles are going to be larger in size than the equator. Let me just make this a little shorter here. So this one is represented by, or this latitude circle is presented by the circle here. Okay, what else do we have? Where are the longitudes? This is, again, this is our principal meridian. This is where you are going to cut through. And your principal meridian is going to be projected as this straight line that just happened to be a vertical line, and it's going to go toward the North Pole. How about the other ones? Let's take the other ones. Let's take this one. Let me use straight lines here better. Let's take this one, for example, or the next one. This one here. Where are these going to be projected? Well, these are going to be projected, again, coming from the same point. So they are all intersecting at the North Pole, and here is how they will look like. They are all going to be looking toward the North Pole here. So all are going to intersect at the North Pole, like this. All coming to the North Pole. So we can here say that we talked about two other properties, how the principal meridian will look like, and how the other meridians will look like. One interesting thing here, you see the distortion here. If the cone is touching, or tangent to the Earth at the equator, then the further you go up or the further you go down, there will be distortion. But you look here, when you go up, the distances between if you look here, the distances is changing. So that means there is going to be distortion, the distances between the latitudes. While if you look tangent here, these distances between the longitudes is constant. So that's one or two other properties. Distances between the latitude circles are changing, while distances, well, that will be 5. Just to make sure when we summarize them. While distances between the longitude lines is going to be fixed. So to summarize here, number 1, the equator is going to be projected as a circle. Number 2, the North Pole is going to be present, and it's going to be a point, and this North Pole is going to be the center for all the different latitudes. So that's why, for all the different latitudes, so that's why we call it concentric circles. Number 3, all the latitude circles are going to be circles in our projection. They are sharing the same center, concentric. Number 4, or well, I have 3 here. Let's call this 3 prime. Number 3 prime is, let me call it 4, or let me call it 7 even. I don't want you guys to get confused here. I'll call this 7. Okay, number 4, all the longitude circles are going to be lines, and these lines are going to go all and intersect. So they are intersecting lines, and they are all going to intersect at the North Pole. Number 5, the distances between the latitude circles is going to be changing, whether you go up or down from the equator. Number 6, unlike these latitude circles, the longitude lines are going to all go and intersect at the North Pole. Number 7, the principal meridian is also going to be a straight line, and it's going to go toward the North Pole. Okay, hopefully that explains it. So let me go back to my PowerPoint. And again, please remember the properties we've talked about here. Let me write it down for you guys so that you do not forget. I'm not going to write the properties. I need you to watch and see. Please remember the different properties. Okay. And same thing, I'm going to copy this and have it here. If you didn't watch this, you wouldn't really get it. That I did on purpose. I didn't put them. Hopefully you can watch and get it. Okay. The other one is the azimuthal, but the azimuthal is simple here. If I got one of these are different azimuthal ones depending on where you place the plane here. Share. So I'm going to share paint again. So if I have the azimuthal one, that's also something you need to remember. How will the latitude longitudes look like here? This is our sphere again. And you have the plane here, or the development surface like this. So what's going on here? Well, first thing is our latitude circles, equator, and then other circles. How are these circles going to be projected? Well, these circles, now you look at the azimuthal, that's very simple to really understand, because this is our eye here, and we are looking from the top. So if you are looking from the top, you'll see the circles all projected as circles. So you'll have all of these as circles, no problems. Here red will be perfect to show. So they are going to be all the latitude Circles are going to be circles, and they are going to be concentric circles. They are all going to be concentric circles here. This is how it will look like. That's the first thing. If you would like to write this as number 2 here. How about the longitude? The longitude lines here. Well, the longitude lines are going to be, if you are looking from here, let me draw the longitude lines first. The longitude lines look like this here. They are circles like this. Then you look here, they are going to be something like this. These are the longitude lines. All lines are going to intersect at the North Pole, and this is how it will look like. That's the third property here. Where is the North Pole? This is the North Pole. Where is the equator? If you are looking from here, the equator will be the greatest circle that you can see here, correct? So this is the greatest circle here will be the equator. So let's summarize the numbers I have here. Number 1, the equator is going to be a circle. Number 2, all the longitudinal circles are going to be lines, and they are going to all intersect at the North Pole, which is going to be a point. Why did I say a point? It's going to be a point for all projections. No, that's not true. Remember, when we had the cylinder, the vertical cylinder, the North Pole was infinity. It was not a point. And then number 3, all the different longitude lines are going to go through the North Pole. Number 4, the equator is going to be the largest circle. Okay, all the latitudes are going to be circles, and they will be concentric. Okay, let's see here the next one. The next one is really interesting, and let me first make sure I get it to the screen, and then I'll show you what I want to do here. Okay, share this one. Okay, how is the projection done? How do we do the projection? So let's take a look here at the Earth, and for simplicity, let's assume the vertical circle like this. And what we would like to get at the end is we'd like to project and get our grid. We would like to get the grid of the latitude, longitude, and based on the information we have now, these latitude, longitude circles are going to be perpendicular lines here. So how does this work? How does this work? Okay, let's assume we have a light bulb here, and let's pick the grid, the latitude, longitude grid on the screen like this. And let's get one of the points here. Let's assume we have this point. Where is and how does this point get projected? Very simple. Let's get one of the light rays, because this bulb is going to emit light rays in all directions, infinite number of light rays. We are just going to pick the light ray that goes through this point, which is this light ray. Oops. How do we project it to the cylinder? Very simple. Just extend this light ray all the way until it hits the cylinder. Just watching if it's projecting. So this is where this point is going to be. Let's pick another point. Get the light ray to it. Project it. Here is where it's going to be projected. Another one. Where is it going to be projected? Extend your light ray until it hits the cylinder. So it's going to be here. And so on. And so on. And so on until we get the map done. Isn't that interesting? That's very interesting, at least to me. Let's go to the next one. If I have a conic, how is it going to be, or how is it going to be developed, or how is the projection going to be here? Let's pick a point. We have the center here. We have the light ray or the bulb here. Let's get its light ray and then extend it. This is where it's going to be on the cone. another point, extend the light ray, and then you get it on the cone. And then we have another point, shoot it, get it on the cone, and so on, until you project all the different points. Now, which when we go downward, we cannot project the south pole, because if you have a light ray, it's not going to intersect with the south pole. Same thing when we had it with the cylinder, we can't really project both the north and the south poles. That's how it works. You see, this is how we do it. Now, of course, we don't really do it this way, but that's interpreting the math. That's just visually showing you the math. There is math involved into it. You will see some of these. I didn't really get all of them in the homework. I just picked 2 map projections to show you how this all is translated into math equations. And I picked hopefully the simple 2, or at least the ones that I think they are simple. And then you get your map done. Okay. How about the next one? The azimuthal projection. This is the center. This is where your light bulb is. And then you have a point on the Earth. And then you have a light ray going from the center to the point. Extend the light ray. This is where the point is going to be. And in 3D, of course, it's going to be a point. Another point, and so on. You keep projecting the points. Again, mathematically, it's done. I'm just showing you, don't want to go all the way through the equations, but this is how it looks like. Because again, it's not just to make it simple or to make it difficult. It's because all these models are already implemented in different softwares. ArcGIS, for example. If you give it the map, you ask it to project it, it's going to project it for you. You can write your own code. You can use a lot of tools, but you need to understand what's going on. You need to understand the differences between these models. All the way until you get the Earth looks like this. All the southern hemisphere is not going to be projected because you are looking upward or you are projecting upward. There are for sure other ones that will do it for the southern hemisphere. Talking about the azimuthal projection in particular, I said that you put the source or the center of the projection at the center. Well, that's not always true. We have 3 different models. And maybe write down that these 3 models, the way I'm presenting them here, is very important for us. That's very important. I might ask you questions, which one present which one? Like, which one is the stereographic versus which one is the orthographic? Or which one is the gonomic? So the gonomic is the one I just showed you, the center of the light or the center of the projection. The bulb is in the center, and then you emit the light radially from the center. And this is how it will look like. The shape wouldn't change. They are all going to be concentric circles, and all the longitudes are going to be intersecting lines here. However, the size and the scale is going to be different. Stereographic, we put the center of the projection or the light bulb here. This is the center. And then when we project, it's going to look something like this here. Orthographic, there isn't really a light source. That's where the name ortho is coming from. We just project ortho. We just project perpendicular to the equator. All the projection lines are going to be okay. I'm not sure if this showed into your screen. There was a connection that's showing, but all the lines are going to be perpendicular to the equator. You see the lines here, all perpendicular and parallel. Parallel and perpendicular is an ortho. Ortho map is just looking at the Earth from the top or looking at the surface from the top. So you have all the different projection lines parallel. Stereographic, we put it here and then we project from this center here. So make sure also the properties of these 3. Let me go back to the PowerPoint. Okay. I'm not sure. I got a message here that screen sharing stopped. So maybe I just pause here. Just I want to mention again, make sure, where is it? I think I have it somewhere here. Yeah, I'm going to write it here also. Please remember the different properties of these models. I'm going to test you on this. I had it here. I talked about it. Hopefully it's clear. If you have problems, again, I'm going to have the office hours and the different ways to communicate, but that's very important for us. Okay, let me pause here, stop recording, and then I'll come back in